Hi everyone! In this talk I will be going over the latency counting system in the SUS hardware design languages, its goals and how you can use it in the SUS code yourself. So the main abstraction for registers within the SUS language divides them into two categories. We have state registers, which are really meant for implementing cycle-to-cycle functionality within your hardware. And then there are latency registers, which are there purely to meet timing and to satisfy the clock speed requirements that your design requires. I will be marking them in the designs as blue and yellow registers. So as an example of state registers, they are pretty similar to how you normally use registers in non-programming languages like Verilog or VHDL. You annotate them with the state keyword before declaration and they can have an initial value. And here we've used them in a module that computes the Fibonacci sequence, one term per cycle. So it starts at 1, then 2, then 3, then 5, etc. There's not much to say about this example, so yeah. Then we'll move on to the latency registers. So here I have an example of a module that computes the 17th power of some number that you give it. It does this by simply multiplying it by itself 16 times and then multiplying that by the original. Now, the intention for the latency counting system is for the programmer to first write their hardware without any pipelining and then simply add registers along the pipeline where required by simply adding reg keywords before statements. Of course, this requires that adding latency does never impact the functioning of the design, aside from, of course, delaying the outputs by a bit. Which is our main design requirement of the latency counting system. In this case, the compiler solves this by adding 2 more registers on the other branch to keep all of the logic in sync and then produce the output after 2 clock cycles. Now we also have our module's inputs and outputs. To keep our hardware as generic as possible, we allow full freedom on the absolute latencies of the ports. So for instance, if at some given cycle we receive our 4 factors here, then 2 cycles later we receive the associated add2 value, and then in the same cycle produce the product, and the next cycle produce the total. You may notice that in the source code on the left, we did not actually add any annotations to say at what absolute latency all of these should be provided. These are for the most part inferred by the compiler. And it does this pretty well. There are some edge cases in which it can't, but in the vast majority of cases it can figure them out. But if you do want to override them, it is possible to do this with the latency annotations. So here we have a module which would normally just encode a wire, and we have forced it to synthesize 5 registers here by adding an absolute latency of 0 and an absolute latency of 5 to our input and output. Having these latency annotations allows the programmer to save the compiler where it needs to, or to exactly specify the hardware as they would desire it. Moving on, another feature of the latency counting system is that it allows to have multiple interfaces of modules. So in this case we are using a FIFO which has a write interface and a read interface. And the logic behind having multiple interfaces is, of course, as you can see, the ready, valid and data port on the left, they are all quite correlated. Like a ready signal at cycle 0 produces or corresponds to a valid and a data signal 3 clock cycles later. And the same can be said on the other side. But between them there isn't such a direct cycle-wise correlation. Now we'll dive into how this module is implemented, like how do we cross this this interface barrier. So here on the left you again see the write interface and all of the ports and latencies that are associated with it, and then on the right you see the read interface with all of its. In the middle you see a dotted line which represents the latency barrier, or the interface barrier, sorry. And when wires cross this barrier, you can see this with the white triangle. Basically, the latency counter discards all latency information up to that point, and it basically, treats both ends of the wire as a separate wire. Of course, this requires the programmer to think about how this connection happens, and to make sure that the hardware is designed properly. So this is the one place where the programmer does have to care about the latencies, but in the most difficult cases this should be handled by the standard library. Some other things you may notice in this module is, for example, we've added an additional latency register after the comparison to the slack value. This was that this is like a complicated operation to do. Having a latency register there would be nice, and it shows how we can combine both latency and state registers in one module. You can also see an offset block there. This is a standard library component that doesn't cut the latency, but just changes it by a fixed amount. And this allows us to give the right side of the module some extra slack between the ready signal and the write signal, so that they can pipeline it a bit. You may also notice that this looks eerily similar to a clock domain crossing. And indeed, at interface boundaries is where the sus language performs its clock domain crossings. This of course has to be handled with special modules to specify exactly how a clock domain crossing is done. So that was my talk. It was very short and I could only scratch really the surface of the latency counting system. But if you want to learn more, feel free to discuss it with me afterwards. And here you can see the link to our repository of the compiler. Thank you all for listening, and see you.